Welcome to a video on solving absolute value inequalities. In this video, we're going to consider inequalities with the outside solutions. That means that we're going to look at understanding absolute value inequalities of the form absolute value of x is greater than or equal to a, and absolute value of x is strictly greater than a. This is where a just represents any real number. Let's get started. Let's look at the definition of the absolute value inequalities for the outside case. For any real number x with a greater than or equal to 0, if the inequality is of the form absolute value of x is greater than or equal to a, then the solution is x is less than or equal to negative a, or x is greater than a. If the inequality is of the form absolute value of x is strictly greater than a, then the solution is x is less than negative a, or x is greater than a. While these two inequalities look and sound very similar, there is one subtle difference. In the first inequality, we have absolute value of x is greater than or equal to a. When you have the greater than or equal to sign, this includes the endpoints negative a and a. For the second inequality, absolute value of x is strictly greater than a. The strict inequality excludes the endpoints negative a and a. There is a special type of these problems where the solution is all real numbers. If you get absolute value of x is greater than or equal to a negative number, or the absolute value of x is greater than a negative number. This is always true because the absolute value is never negative. So in this case, the solution would be all real numbers. For example, the problem absolute value of x is greater than negative 5. The solution is all real numbers. Since the absolute value is always positive, it will always be greater than negative 5. Before we look at how to solve these types of problems, let's make sure we understand the solution set. A solution to an absolute value inequality is usually not just one number. The solution set contains every value of x that makes the inequality true. Typically, this includes infinite many solutions. For these type of problems, the outside solution set typically includes two regions. You'll see what I mean when we get to the example. In math, whenever a problem has infinite many solutions, there are usually many ways to describe the solution set. We will express solution sets using inequality notation, interval notation. Remember that we use square brackets for regular inequalities, less than or equal to or greater than or equal to, and round parentheses for strict inequalities, less than, greater than, and positive and negative infinity always receive parentheses in interval notation. We also graph these solution sets on the number line where we shade all of the included values of the solution set. Closed dots coordinate with regular inequalities to denote the endpoints are included. Open dots coordinate with strict inequalities to denote that the endpoints are excluded. Let's look at an example. The absolute value of x is greater than 4. So using the definition, we could rewrite this in inequality notation by saying x is less than negative 4 or x is greater than 4. So the solution set is in two pieces. That's why we say that these outside solution sets usually include two regions. Because they include two pieces or two regions, if we rewrite this in interval notation, we would have two intervals, negative infinity to negative 4, along with 4 to infinity. Notice that both negative 4 and 4 have round parentheses. That's from the strict inequalities. Positive and negative infinity always get round parentheses. If we wanted to graph this on a number line, we would start by plotting open dots at negative 4 and then shading where the x values are less than negative 4. This would be to the left. For the other piece of our solution set, we would use an open dot at 4 because of the strict inequality And then we would shade values of x that are greater than 4. So we would shade values to the right of 4 on the number line. So here we have the same solution set displayed 3 different ways: inequality form, interval form, and graphically. Notice that each of these 3 different ways have 2 pieces or 2 regions to it. Now let's go over the steps to solve absolute value inequalities while we work the problem 3 times the absolute value of x minus 9 is greater than 6. The first thing we want to do is to isolate the absolute value expression. We want to get the inequality into the form absolute value of x is greater than or equal to a, or the absolute value of x is greater than a. Let's go back to our problem and isolate the absolute value of x. The first thing we need to do is to add 9 to both sides. So this will give us 3 times the absolute value of x is greater than 15. Now let's divide both sides by 3. This gives us absolute value of x is greater than 5. The second step is to check the value of a. If a is less than 0 or negative, then the solution is all real numbers. This would be that special case I mentioned earlier. In this case, our value of a is 5. This tells me that we have a solution, but it's not all real numbers. We need to keep going. The third step is to rewrite the absolute value inequality as a compound inequality. If you have absolute value of x is greater than or equal to a, then rewrite it x is less than or equal to negative a, or x is greater than or equal to a. If you have absolute value of x is greater than a, then rewrite it as x is less than negative a, or x is greater than positive a. It looks like we have the strict inequality, so we would rewrite absolute value of x is greater than 5 as x is less than negative 5, or x is greater than 5. The fourth step is to solve the compound inequality, where we would isolate x for each piece. However, this is already done for us in this problem. X is already isolated in the expression x is less than negative 5 or x is greater than positive 5. Step number 4 does not apply to this problem or the rest of the problems in this video, but you would need to do it if your problem was a little bit more complicated. Step 5 is to graph the solution on a number line and write it using interval notation. Here's my number line. Since the inequality has 2 pieces, there will be 2 pieces that we need to sketch on the number line. Let's take the first part, x is less than negative 5. I'm going to need to use an open dot at negative 5 since we have a strict inequality. We want values of x that are less than negative 5, so my shading will go to the left. This includes points like negative 6, negative 7, etc. Now let's graph the second piece where x is greater than 5. We're going to have an open dot at 5 since we have a strict inequality. We want values of x that are greater than 5. This means I need to shade to the right for numbers like 7, 8, 9, etc. Now let's go ahead and rewrite each piece of this compound inequality in interval notation. For the piece on the left where x is less than negative 5, we would write that as negative infinity to negative 5. Negative infinity would receive a round parenthesis, and negative 5 would receive a round parenthesis since we are dealing with a strict inequality. This is going to be in union with the interval that describes the next piece, which is where x is greater than 5. That would be from 5 to infinity. Infinity once again receives a round parenthesis. 5 receives a round parenthesis here because of the strict inequality. Now we've written our answer 3 different ways. Let's finish this video by solving a few more examples. Let's solve the problem 7 times the absolute value of x plus 21 is greater than or equal to 35. Let's start by subtracting 21 to both sides. So we get 7 times the absolute value of x is greater than or equal to 14. Divide both sides by 7 to isolate the absolute value of x. We get the absolute value of x is greater than or equal to 2. Now if we check our value of a, we can see that a is positive. So we know this has a solution, but it's not all real numbers. Let's keep going. If we rewrite this into inequality form, it would be x is less than or equal to -2 or x is greater than 2. Now let's graph it on the number line. Let's take a look at the piece on the left first where x is less than or equal to -2. Since we have a regular inequality with that equal bar, we'll be using a solid dot at -2. Then we want values of x that are less than -2, so we'll be shading to the left here. Now let's do the second piece where x is greater than or equal to 2. Once again, we're going to have a solid dot at 2. We want values of x where x is greater than or equal to 2, so this means we need to shade to the right. Now that we've shaded both pieces on our number line, let's rewrite these using interval notation. For the first interval on the left, where x is less than or equal to -2, using interval notation, this would be from -infinity to -2, with the square bracket on -2 since it is included in the interval. -infinity gets a round parenthesis, as always. This will be in union with the interval that describes where x is greater than or equal to 2. This would be from 2 to infinity, with a square bracket on 2 since 2 is included, and infinity, as always, gets a round parenthesis. Finally, let's take a look at this last problem. 9 times the absolute value of x plus 5 is greater than 1. Let's start by isolating the absolute value of x. To do this, we need to subtract 5 to both sides. This leaves us with 9 times the absolute value of x is greater than -4. Divide both sides by 9. We're left with where absolute value of x is greater than -4/9. In this case, that value of a is negative. Absolute value of x is always going to be positive, so this absolute value inequality has a solution of all real numbers. If we wanted to graph this on the number line, we would shade the whole entire number line. To represent this in interval notation, we would write the interval from -infinity to infinity with round parentheses on both, since positive and negative infinity always receive parentheses. That's it for this video. Thanks for watching.